So today we are going to finish depth perception. And then on Wednesday, we are going to talk about color perception. And probably I will not finish because it's a lot, and I'll add either to next week or probably I'll add, I'll add an additional recorded lecture. So depth perception is interesting. There is a lot of stuff, and it's not complicated. So the main idea is that the system cannot not interpret, and we've seen it all along the way, that our system cannot force a meaning upon the stimuli around us. The sensation of 3D, of three-dimensional world, is something that it's internal. It's a sensation. It's an internal interpretation of our system. And dark suddenly. Sorry, let me undark myself. It's an internal interpretation that doesn't exist. We only have for most of us, only two-dimensional flat pictures from which we interpret this sensation of three dimension. If with one eye we have a diminished sensation of three dimension, but if you spend a while with only one eye, this feeling comes back. People that have only one eye, they do have, well, it's hard to say that because we cannot compare, but this sensation comes back. If we that have two eyes suddenly close, we feel suddenly everything is flat. But beyond this sensation of 3D that we have, for instance, when we watch 3D movies, this sensation is not necessary for us to perceive death and to walk around without bumping into things. So the main problem is how to infer three-dimensional space from only two very, very similar two-dimensional images. So we have a lot of convergent cues, convergent processes that we bunch them together. They are redundant. Many of them are independent from each other, and sometimes they are even conflictual. We'll see some examples. So roughly speaking, they are divided, all these cues from which we infer three dimension, they are defined, they are separated as oculomotor, that's internal, monocular, everything we can, all the information we can gather with only one eye, and binocular, things that we can only, information that we can only gather, interpretations we can only gather from two eyes. Monocular cues we gather from both eyes, obviously. These are more or less everything. We'll begin with oculomotor. Monocular is oculomotor. Here there is a mistake. Instead of accommodation, it should be oculomotor. I'll fix it later. And then we have pictorial cues and movement cues. So oculomotor are internal, pictorial, they are from the stimuli, and movement also. The different cues, these different processes, they are more or less efficient depending on the distance. For appraising different distances. We'll come back to this later. So let's begin with oculomotor. We have two sources of information, convergence and accommodation. Convergence means that whenever we focus on an object in the distance, our two eyes, they converge or diverge in order to place whichever object of interest we are fixating on the fovea. So these movement, the convergent movement, they are made by extraocular muscles around the eyes, and they can be voluntary or involuntary. Accommodation, they are, I'll explain soon. Accommodation, they are a consequence of ciliary muscle contraction, which are involuntary. And what they do, they squeeze our lenses. So when the lens is squeezed, it, how do you say, it deflects light more than when it's not squeezed, okay? So people with myopia, nearsightedness, they have a problem in the system and the focus falls away from the retina. That's why people like me uses corrected lenses. Hyperopia with its farsighted is the opposite. They can focus easily on close things, but not for far things. Astigmatism is a completely different story. I told you, I think, 2 lectures ago, is when the lenses are not here, they are here. When the lenses have a small deformation larger than everybody has a little bit of astigmatism. Some people have more. Okay, so both convergence and accommodation are movements by muscles, voluntary or involuntary, that are controlled by our brain. So our brain also uses that information in order to infer the distance from our eyes of the object we are fixating on. So there are two theories that they are not mutually exclusive. One is that we use proprioceptive feedback, meaning that our brain, the system sends an order to the muscles to do something, and then the muscles sends back this information, and then the system uses. The other one is that the brain is already sending the information, so it has this order. It doesn't need the feedback itself. So it's almost a nuance. Efferent commands are everything that the central nervous system sends to the muscles, and afferent is what comes back. Okay. So this is the angle, the convergent angle of the eyes according to distance. So we can see that when we are looking at something really close, our eyes, as we all know, they really cross in order to put the object on both foveas. And the further away, the less they diverge. But as we can see, after some 5 meters, there is hardly any difference. They become almost parallel, which means that the movements, these convergent movements of the eyes, is mostly useful for near objects. up to 5 meters, more or less. The same for accommodation, okay? We can see here that at a certain point, when there is no difference if you're looking across the street or 100 or 500 yards away, the lenses are relaxed and they are almost flat, and the eyes are parallel. Okay, now pictorial cues. I'm going to go as fast as I can because they are very simple. They are used, these are not the main information that we use for depth. The oculomotor, it's mainly for, it's convergent information. Most of the information we use are the pictorial cues. They are monocular, meaning one eye by itself can use this information. So by looking at this picture, I think we have everything. Occlusion means whatever is further away is occluded by a closer object. It is obvious. We know from experience that the more or less the relative sizes of objects that we know, of a person, of a lamppost, of a mountain, relative height size is almost the same. Perspective convergent means that from our point of view, two parallel lines, they get closer and closer, they converge towards the horizon. Atmospheric perspective is the haziness of far away objects, because there is more air between us and the object. Texture gradient is that we'll see soon. Shadows and familiar size. I'll go one by one. Now, occlusion, the first one. Look. This is so occlusion. Whenever something occludes, we feel that it's closer. So here, even though the circle is the same size, we feel that it's getting closer to us, right? So that's the first example when we interpret wrongly. We must interpret something, and look how strong is the occlusion cue. We have the impression, the feeling that it's coming towards us. Familiar sizes. So we know that a quarter is larger than a dime, and if we, so there is an experiment that if we take the clues away from all other visual stimuli, we feel that a dime will feel the dime closer than the quarter, because we know it's supposed to be smaller. As I said before, the further away something is, especially from far away distances, there is this haziness. Light is filtered out by the dust in air, and it actually filters out some ranges of wave-light. That's why usually it looks gray or bluish. Texture. So, for instance, when we have parallel lines, they are perceived as convergent towards the object. The same for sizes, density, etc. These are obvious stuff, right? The Ponzo illusion. So here we have familiarity against perspective. So it's the same size, this animal, which I don't know what is it. The size of this animal on our retina is the same, but because of the perspective, feels that this one is much larger. It's called the Ponzo illusion. The Müller-Lyer illusion. So from these two lines, which one feels larger for you? Well, you don't have to answer this one. It's a known one, a known illusion, and they are the same size, but the illusion is very strong. Why it happens? Well, one interpretation is that we cannot not try to make sense of this, and we use our holistic interpretation of space. So things that have this format usually are closer, are inner spaces, and these are far away spaces. So we make the opposite inference that this is, let's say, inside the room, and this is the side of a building, so this must be larger. Emmert's law is proposes that perceived distance from an object is the calculation from the size of that object in our retina by the perceived size of that object. So the only physical objective measurement here is the size on the retina. This is perception and this is perception. So when we perceive something very far, we will perceive it as smaller, and the opposite. So one known problem for pilots is the whiteout effect. When you have low visibility from above, you may perceive an object as smaller than it is. No, as larger than it is. As smaller than it is, and then the pilot may mistakenly think that the ground is far away, still that the plane is still higher than it actually is. And there are many accidents of pilots landing thinking that they are still far away, and they crash onto the ground. Another interpretation, another assumption that we tend to automatically use is that light comes from above. So if we look at this picture, we feel that this is a crater, right? That this is a hole. Now, if we flip the same image, suddenly it becomes a hill with a hole inside. It's the same image, yes? It's just upside down. So that's because we assume that light comes from above. So this is the shading determines our interpretation. Here, all these squares have the same size, but because of the distance of the cast shadow, we feel that this is closer to us. This is a strong one. It's a known illusion. The Ames room, there is here in New York, there is a museum of illusions, visual illusions. And they have this room built over there. So we cannot not feel that this child is a giant child, or this is a minuscule child. Now look, even when we know that it cannot be, we cannot not perceive it. We know that it's an illusion, the room is but we cannot not perceive that one. I find it incredible. So this is the Ames room. Okay, so how is it built? It's slanted, so this window is smaller than this window. This window is larger, and it's from the point of view of the observer, this wall is slanted, and this point is higher. Okay. What time is it? Let's move on. Let's move to movement cues, which are monocular. We still use it by both eyes, but we can use this information with only one eye. So motion parallax is the interpretation of relative distances of objects according to their relative movement on our retina. So if your eyes, your head moves the same distance, a close by object will have a larger displacement on your retina than if you move the same distance but then a further away object when you move the same distance. Okay, so this object, you move the same distance. This object was displaced this far, and this object was displaced this far. So you know this feeling when you travel. We can really see it. So these fellows here, they have a very small displacement in our retina compared to this. So we use this information unconsciously to infer the relative distance of each object. In cartoons, this is a very strong cue. We use it, we cannot not use this to infer, and even simplistic cartoons use it for us to, yes, you understood. So the same idea is the deletion and accretion, which is where it's occlusion during movement. So when this is accretion, this is deletion. When we are moving, we infer from the distance. Okay, so motion parallax, deletion and accretion is useful for us for close by and medium distances. When it's too far away, it's less informative. Occlusion, wherever it is. Relative size, we use it a lot. As we said, Oculomotor internal information is mostly used for close by objects. Relative height for far away, and obviously atmospheric perspective for very far away. Relative height and relative size is something that we actually can learn very well in the army. We learn how to estimate distances very well by according to the size of an object. Even with one eye, we use fingers, and I'm not part of them anymore. In the army, you can assess distances very well. So for instance, why is it important? Because sorry, it's a little bit. So when you the ballistic movement of a projectile, it falls on the way. So you have to know where to aim according to the distance. So that's why you have all these measurements inside the scope. Not only theoretically you need only the X, right? But different scopes, they have all kinds of things like that. Well, with that you can estimate pretty well. So this is for a person. Sorry, it's a little bit creepy that I show you that. The shoulder width of a person at 25 yards, it's this distance inside the scope and this distance. So a sniper, for instance, he has this table in his pocket, and then the sniper knows depending how far away it is, how higher than the target it aims. Okay, we are moving to binocular cues. What time is it? Half an hour. Oh, I'm doing faster than I thought. Okay, binocular cues are those that we need both eyes to interpret. Like it's information that we can only use when we have two images that are slightly different from each eye. And the main story is, as I just said, binocular disparity. So our eyes are very close by, enough for us to use it rather effectively, but the larger the distance between the eyes, the more information you have. And that's how we can also fake the sensation of 3D by presenting different images to each eye. So each eye, because of this distance, as you can see here, the retina has a slightly different image. We can see mainly here, right? And we can demonstrate, well, you all know this, right? Put your finger in front of your face, look at any object, and then you close one eye, and then you open the other one, and you see that you have a different picture. So how is it done? The system maps corresponding points on the two retinas. Everything in comparison, in relation to the fovea. So corresponding points on the fovea are those that fall to the same size of the fovea with the same distance. Okay. So all objects that are in the same distance from your fixation point. So imagine you are fixating on an object 10 yards away from you with a certain convergence. All objects that are 10 yards away from you, they fall on corresponding points on both retinas. They fall. So if you're fixating on this point, and Susan and Harry are the same distance from your eyes, Susan will fall on corresponding points on the same retina, to the same size and the same distance on the retinal area. Okay, the same for Harry. So this imaginary circle around you, you are the center of the circle, so all objects with the same distance from you, is called the Horopter. So all objects that are on the Horopter, they fall on corresponding points, which means that there is no disparity between their position on the two retinas. So here, again, another example. The person is fixating on Julie, and the tree is the same distance from the person, that is, it falls on the Horopter. So the tree falls on the two retinas to the same size of the fovea, to the left side, and the same distance. So for non-moving objects, it's the same like the motion parallax. The motion parallax it's information we can use with only one eye, that is depending objects that have that are in different distances from you. When you're moving, their displacement on the retina is different. The further away, the smaller the displacement. So for non-moving objects, we use a parallel calculation by using the difference of the objects in the two retinas. And this is binocular disparity. So all objects that are not on the Horopter, meaning all objects that are either closer or further away from the object you are fixating, then they fall on non-corresponding points, meaning that their points on the retina are two different sides of the fovea. So in this example here, the fixation is on Julia. Bill will fall in one eye to the left side of the fovea and to the right side of the fovea in the other eye. Dave, that is even closer than Bill, will fall even further away from the fovea to either side. So the terminology is that for objects that are closer to us, they have cross disparity. Meaning, why cross? This is only arbitrary terminology. Cross disparity because in order to move your fixation from Julie to a closer object, you have to cross your eyes. You have to converge your foveas. To move, to fixate on objects further away, you uncross, you diverge your eyes. So this is called uncrossed disparity. Okay? Okay, let's try this question. Okay. All right. So most of you answered B and D. So while you are fixating on the blue object, which is on the Horopter, obviously, the Horopter, the definition of Horopter is where you're fixating. The green object, this is green, I'm colorblind. So you're fixating this, so this must be the green one. The green will have uncrossed disparity, so it's either B or D. And the blue object will have zero disparity because that's the object you're fixating. It's on the Horopter. It falls on the fovea, exactly. So the answer is D. Okay. And is it clear? Any questions? Anyone doesn't agree with me? No. Is it clear, anyone? All right, so in this case, the green object falls on the Horopter, so it's E, 0 and 0. There is no binocular disparity between the position of the green object for both on both retinas. They are both this distance from the fovea on both retinas. All right. Okay, so 3D interpretation is not, again, it's not an existing set of stimuli. It's an interpretation. It's not the average of two image. It's not that you take two image, the system takes two image and averages into one image. That would be a blur. It's an interpretation that doesn't exist from two different images. It's neither image. It's a third thing, and we feel it when we feel three dimension. It's not an image. It's a feeling. It's a sensation, and we can fake it. Actually, we can fake it pretty easily. And it has been done forever. All we have to do is take two pictures from slightly different positions, which is supposed to be the difference, the distance between our two eyes, and then we show it, each one to one eye. As simple as that. Has been done forever, since there are pictures. This is the stereoscope. Another way to do it is to show the same image that is filtered to either eyes, and that's nowadays, when the 3D movies, they use polarized lenses. If we have time in the end, I will explain what is it. But a simpler way that works very well is you take the same picture twice with the same displacement. Let's say we take these two pictures, and from the distance between two eyes, the angle, and then one you paint red and the other green. And if you use one red and one green lens, only one of the pictures will reach your eyes, because the green picture will be filtered by the red. Next lesson, next lecture, we will understand exactly what's this filtering, and but intuitively you can understand, right? So with the red filter, the green picture doesn't reach the retina, and the opposite from the red. Now, I remind you that it's not that each eye sends to one hemisphere. It's each side of both retina, the right side of both retinas reach the right hemisphere, and the left side to the left hemisphere. But it doesn't matter. So each one picture to each eye, and then we have the perception of 3D. And it's very strong. It works pretty easily. Even these pictures that I'm showing you here, if at home you have one of those glasses and you look at it, it will work. If you have a cellophane, red and green, and you put in front of it, it will work. You can even take a clear plastic, or take your glasses and paint it with the marking one that you can clean afterwards. It will work. You can also do by crossing these two pictures, for instance, you can try later. If you get closer and you cross your eyes in a way that both pictures reach the fovea or corresponding points in your retina, you will perceive 3 dimension. This is a kick that in visual labs, it's like everybody learns to do it. Concerning convergence, there are people, including myself, that can move the eye voluntarily. I can move only one eye like this and like that. I will not show you because it's really creepy. But you can learn to do it. Okay. We have 15 minutes. Good. So fusion occurs when the picture falls on an object falls, the same stimulus falls on corresponding points. Fusion is the process that we use. It's not averaging, it's fusion we use to have stereopsis, to attain this feeling of 3 dimension. And suppression occurs when the system cannot make sense, when the system cannot fuse, and it can happen in some situations. I'll explain in a minute. Binocular summation is when you have a threshold for light or for resolution, that with 2 eyes the threshold is lower than if you add the threshold of both eyes. So when you present, if you remember, when I told you about the FFA, no, I don't have it here. So in that experiment about face, when they discover the area in the brain that is really active when we perceive faces, so they showed exactly this stimulus. They showed this image to the participants with a red and blue and green lenses. So each eye, both eyes see this thing together, but each eye sees only one of them. So what happens here is that now we are looking at this, we see this superimposed image, but if we were using a red and green glasses, only the face would reach one eye and the house would reach another eye. And then we cannot see them both at the same time. It's a strange feeling. You can either see the face or the house. In the beginning, you cannot control. And at a certain point, you can even control which eye is dominating the perception, but you cannot fuse them together. You cannot perceive them both at the same time, because we cannot not interpret something that doesn't make sense. The system cannot not choose one meaning for what we see. It's like many other illusions that we saw with the vase and many other, that we cannot have two perceptions that have meaning at the same time. And this is suppression. Suppression is when one the information from one eye or from one area is suppressed in order to choose one meaning. Now, one interesting thing is that we can learn to suppress. So, for instance, going back to a sniper, we learn the snipers learn to shoot with both eyes open, and you really learn to choose which eye. And they have completely two different images. One is through the scope, and the other one is here. Snipers learn to do it because you have more information. If you have only your scope, then you lose everything that is happening here. And with two eyes, you still perceive it. Something moves, you can move. It's considered an attentional effect, but you really learn how to choose only the information from one eye. How does it happen? Now, one problem that happens, the suppression occurs. Suppression must occur when the images are not corresponding enough. So, for instance, people that have strabism, meaning the eyes cannot, it can have many sources, but muscular, neurological, drugs can do it, and other stuff. So the eyes fail to put the same object in more or less corresponding points in the retina. So the brain must choose which one. It cannot fuse the two images. They are too disparate. So when children have it, it must be corrected, because if it happens during critical stages of development and it's not corrected, then the brain ends up choosing only one eye, and the other eye becomes more and more suppressed and becomes dysfunctional. It can be corrected with surgery and other ways. We all know children with a patch. The patch closes the good eye, so it forces the system to use the bad eye. When it's not corrected, it can end up in amblyopia, which is a developmental deficiency that is caused by, usually it's a muscular problem, and the system fails to learn during the critical stage to fuse these two images. They are too disparate. One last point, how does it work? Technically, what we know is that, if you remember from 3 lectures ago, in our visual cortex, our cells, our neurons, they are organized, they maintain a retinotopic organization. So not only close by, neurons that are close by, their receptive fields are close by in the retina, but also we have layers of neurons that correspond to the right eye and to the left eye. So what happens is that when so the system can vary at a certain point, choose to suppress one eye involuntarily, in the case of amblyopia, or voluntarily, in the case of the sniper. That's it. We've done. Questions? So the question is, whether 3D plays on both eyes. It directs to each one specifically. I don't understand the question. So we use the difference between the two eyes, the images, the 2D, two-dimensional images, the difference between the two-dimensional images from the two eyes in order to infer a representation that doesn't exist. It's not a physical thing, a representation of the world which we feel as three-dimensional. Am I answering it? Let's put it this way. If you, with only one eye, you cannot fake three-dimension. There is nothing you can do. One eye cannot gather any kind of information in order to build this internal feeling of three dimension. It doesn't mean that you cannot perceive three dimension. Absolutely, yes. You can watch the same movie in 3D and in 2D, and you understand exactly what is where. The only difference is that feeling that we have. If you, as I said before, if you close one eye, after a certain time, you will regain the feeling of 3D. I don't know if entirely, okay, good. I don't know if entirely, I don't know, I suppose, it's hard to say because it's an internal feeling, but I don't know if people that were born in only one eye, whether their feeling is commensurate to people with two eyes. But I know that if you, even as an adult, I imagine that as a children, even easier, but as an adult, if you close one eye for a while, the feeling of 3D will gradually come back. Anyone else? Something?
I was wondering if you could re-explain the binocular summation.
The binocular summation. Actually, the binocular summation, I decided to put it here out of a whim because I'm not sure it's really related. The idea is that, let's say that both eyes, let's say that the minimum threshold for perceiving a object is 3 photons, okay? One eye. So for the receptors on your eye to perceive a given size of object, the minimum amount of light that has to reach your retina in that area is 3 photons. So theoretically, with 3 photons on each eye, you would perceive it, right? When you have one eye, if it's 2 photons, you do not perceive. 2 photons, you do not perceive. With 2 eyes, you can perceive it with 2 photons.
That makes sense. Thank you.
You're welcome. and it's not really related to depth perception. I shouldn't have put it here. Let me explain to you what's the polarizing glasses. So imagine, nowadays when we see 3D movies, the glasses are not green and red, they are clear. But what they have is a polarizing filter. The idea of we also have polarizing filter for sunglasses, and also people that deal with photography know it. So light is a wave, right? It's a wave that goes like this. Now, in a natural setting, the waves, they go in all directions. So they can go like this. Can you see me? Yeah. So they can go like this, they can go like this, they can go in any direction. Polarizing filter allows only, I don't know how to show it, allows, let's say this is a polarizing filter. It has horizontal, imagine a grid. So if light comes like this, it will pass. But the same light that comes like this, it will not pass the filter. So if you, in each eye, for each side of the eyeglasses, you put a polarizer, let's say vertical, horizontal and vertical, then you can send this two different pictures to each eye according to the orientation of the light, which is much more effective than having green and red, because red will filter not only green stuff, will filter other colors as well. You see everything darker. And with the polarizers, with two different polarizers, you can send a much richer picture to each eye.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.